Now that we have this idea that acids don't dissociate fully, bases don't dissociate fully, we actually have another concept related to that, and that is percent ionization. So how many ions are we creating from what we started with originally? So we will calculate percent ionization for weak acids from pH and molarity. We'll also calculate percent ionization for weak acids from pOH and molarity. And finally, we'll calculate percent ionization for weak acids from Ka. So what is percent ionization? It measures how much of the acid has dissociated at equilibrium. So percent ionization is equal to the hydronium ion at equilibrium over the acid concentration times 100. So it's literally a ratio, how much of this dissociated. And the higher that dissociation constant, the stronger the acid. So absolute highest would be something like HCl, which dissociates fully, so it would be 100% ionization, and everything else is going to be less than that. Anything that's not a strong acid is going to be less than 100. So let's talk about how we implement this. If we are given a pH of 5.24 and a 1 molar solution, what is the percent ionization? So here we have in the problem our H plus concentration in disguise because we have pH. So pH is the negative log of H plus. We do 10 to the negative 5.24 and we get 5.8 times 10 to the negative 6th. So in case you're wondering about the sig figs here, pH and pOH only count the digits after the decimal point as significant. Before the decimal point, it does not count. It's because it's the order of magnitude, essentially. When you take the log, the thing out front is the order of magnitude. And we don't count that in scientific notation. The 10 to the negative 6 doesn't contribute to the significant figures. It's just the non-zero numbers before that and zeros that count. But you get the idea. Only the digits after the decimal. So 5.24 has two significant figures. So your H plus concentration has two sig figs. All right, so at this point we can plug things into the equation because we have both the hydronium ion concentration and the acid concentration because it's given in the problem. And if we do that, we get 5.8 times 10 to the negative 4th percent. So whatever this acid is, it's incredibly weak. It does not dissociate very much at all. Given a pOH of 3.79 and a 0.25 molar solution, what is the percent ionization of the acid? This is a tiny bit more complicated than the previous problem. We have a pOH instead of a pH. So we can do this problem two different ways, using the relationship between pH and pOH equal to 14, or the Kw equation where Kw is equal to OH minus times H plus. I'm going to use the Kw relationship. So I'm first going to calculate the OH minus concentration. So I take 10 to the negative log of 3.79. And when I do that, I get 1.6 times 10 to the negative 4th molar OH minus. Now I use my Kw equation in order to get back to my H plus concentration. So when I take 1 times 10 to the negative 14th divided by 1.6 times 10 to the negative 4, I find that my H plus concentration is 6.2 times 10 to the negative 11th, which is pretty freaking tiny. Although we measured it in pOH, so maybe this was a base to begin with. Anyway, onward we go. Now we have both parts of the percent ionization equation, so we plug and chug. And in the end, we get 2.5 times 10 to the negative 8th percent ionized, which is pretty tiny. This is a very weak acid, but again, given that we measured pOH, this is probably a base that we're calculating for. But we know we can interrelate the two, right? They're going back and forth. They're in equilibrium. This is valid. This is a thing we can do. Okay, so let's try a different permutation of the problems. Okay, so let's read this one off. If you have an acid with a Ka of 2.7 times 10 to the negative 5th and a molarity of 0.015, what is the percent ionization? So we have a pretty tiny Ka, right? It's times 10 to the negative 5th. That's itty bitty, which means that we're going to have to use an ice table. Here we go with the ice tables again. Really, I'm not kidding. We're going to spend a lot of this term doing ice tables. So we put our initial concentration under HA, and we put 0 and 0 here. So that's the concentration before it dissociated. We're going to subtract X from the reactant side because we're pushing towards products. There's nothing over there. And then we have our summary line for equilibrium. Okay, so we've got the things. And we've got X and X there. And now we can put that into our Ka equation. So we know that Ka is equal to 2.7 times 10 to the negative 5th. And that is going to be equal to X squared divided by, now we have a choice here. Do we think that 0.015 is large enough that it won't matter whether or not we do the quadratic formula here? And I'm going to make the assumption that it won't. I actually did do the math on this, and it comes out that it doesn't. It's basically the same with an error. So we're going to take the shortcut. Okay, so we go ahead and we solve for X, which is relatively easy once we make that little adjustment. And we get 6.4 times 10 to the negative 4th. That is both the molarity of the H plus and the A minus. But we don't really care about the A minus when we're finding percent ionization, do we? No, we don't. So we're going to put that 6.4 times 10 to the negative 4th over the 0.015 multiplied by 100, and we get 9.2% ionized. So this is actually a relatively strong acid. It's not a strong acid, but it is relatively strong to some of the other ones that we've been talking about. And this is somewhere in the neighborhood a little bit stronger than acetic acid, if it were a real thing. But I just made up numbers, so not so much. All right, moving on. To summarize, use the acid and base definitions to fill in missing information about H+, OH-, pH, and POH. And when you want to calculate percent ionization, it's equal to the H3O plus at equilibrium over the HA concentration times 100.